Total porosity, threshold diameter, theoretical diameter, mean pore diameter, you can do a lot of things. A lot of drawbacks also there. So the idea is very simple. I take a liquid, I fill the concrete with or cement paste with that liquid, and I figure out how much of liquid I needed to fill the entire pore structure. That is my porosity, right? How much of material I want to fill in all the pores with my porosity. But there's a problem. Concrete absorbs water. So I cannot use water as a fluid to fill in. I want a non-wetting liquid. The only non-wetting liquid that we know of is not very friendly, not very healthy, but we have no choice. Mercury is the only non-wetting liquid. Problem with mercury? Extremely high density. So you have to squeeze it under extremely high pressure into the structure. Now, you are looking at, in mercury inclusion porosimetry, you are taking a small sample of paste, putting it in a small glass container, filling the container all around with mercury, and then exerting a pressure of a maximum pressure of 414 megapascals. 414 megapascals into a small, this much size of cement paste. Okay? So that mercury under that pressure will enter in and go through all the pores of the material and fill it. So we go from pressure of 1 or 2 megapascal all the way to 414 megapascals, because the smaller pores will be filled with a lower pressure, right? If I have only lower pressure, smaller pores will be. Larger pores. Larger pores will be filled with smaller pressure. But if I have a really small pore, I need extremely high pressure to fill it. That's why you're going all the way to 440. Now, do you have a logical question on something else? On what happens if I compress this thing to 414 megapascals? The material may white crash and fail, right? So is that a problem? Yes. So that is something that I want to make this connection to what I told you yesterday. You have a sample. Mercury is all around the sample, right? You are exerting a triaxial pressure. You are exerting a three-dimensional pressure, not a unidimensional pressure. When I told you about the unidimensional compression test yesterday, I told you what is actually failing the material? Tension because of Poisson's effect, where you have lateral expansion. But if I'm exerting this pressure all around, there is no way for the Poisson effect to happen. Should it fail? That is why in nature, you put all this big building, simple example, right? You put this big 100-story, 50-story building on a rock. You take the rock and test the uniaxial strength of the rock. Can it carry this entire building? Why is it not failing? The rock is confined from all the sides by everything else. The rock or the substrata in which you're building this big building is confined triaxially. It's not confined uniaxially. So number one, when I say the compressive strength, it means nothing. I'm actually ensuring a tensile failure, right? And then you're saying so many things. Concrete is weak in tension. Therefore, I test the compressive strength. But you're getting a tensile failure. You won't tell that to anybody. You say, I can't test the concrete in tension because I can't grip it. Very true. But then every time you're testing in compression, you're failing it in tension. Right? And then you're saying 40 megapascal, 50 megapascal. If the material had a consciousness, it must be laughing. So sitting and saying, this guy is doing the most stupid test on me, getting something else, reporting again something else, and saying all my standards are satisfied. Right? Think about the fallacy. You are trying to apply a uniaxial compression. your test machine says yes, 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 I am applying a uniaxial compression. But then you're bulging out, you're creating lateral tension and shear because of the plater effects, which we should not forget, because you're pushing a concrete with a modulus of elasticity of say 40 GPa with a steel of 200 GPa elastic modulus. And if you remember your structural engineering from somewhere, there is something called strain compatibility that you have to satisfy in any mechanical loading, which you are never satisfying because your 200 gigapascal stiffness plate is pushing 40 gigapascal stiffness plate. That too, the older compression machines are pushing only from one side, not from two sides. Again wrong, because your equilibration of pressure on both sides will take some time before which micro cracks would have formed. So that's why you see different labs will give you different results. All of these variabilities. And then of course there's a lot of variabilities in between your specimens also. Let's switch this off. Give me. There's a lot of variability in between the specimens also. So in mercury intrusion porosimetry, even if you're applying this 440 megapascal stress, you will not have complete failure of these particles, of these species, because you have confinement from all different sides. You're applying pressure from all different sides. Basically, the idea is to squeeze mercury inside. You might have a few cracks, sometimes extra cracks formed when the load application becomes non-uniform. Sometimes that happens, but that is something that we will have to consider in the process. So when anytime you do a compression test, here's what I always tell my students: you do the compression test to satisfy people who are always looking for a compressive strength test, which everybody other than this room wants it, right? When you go for specification approval of a concrete, what's the first thing that they ask? What's the strength? They won't even ask what's the compressive strength, what's the strength. Okay? Compressive strength is not even a strength. What is strength? How do you define strength? Strength is a stress at failure. Theoretically, when something could never fail in compression, what is even a compressive strength? There's nothing called a compressive strength. Theoretically, you talk to a perfect theoretician, a perfect physicist, and tell him compressive strength, he'll say nonsense. When nothing fails in compression, what is a compressive strength? Right? You're failing in other mechanisms. When you're doing compression, you're activating other mechanisms of shear and tension. Things fail in shear, things fail in tension. Okay. And that is why, so for example, if you're building concrete columns, you will never see a compressive failure of a concrete column because you have confining steel also, your steel that's confined. You will see spalling, you will see deterioration, you will see chipping off. That's all because of bad concrete and environmental processes, not because of the compressive load that is happening. Okay? So, thing to remember, compression should not cause failure. If compression causes failure, none of us would be living, because this building is exerting more than the uniaxial compressive capacity of the substrata that this is sitting on. We should be sinking to some underworld already. We should have sunk already. Because it's all triaxially confined, you will have no compressive failure. That's exactly the principle that you have in mercury diffusion process. So you have triaxial compression. So mercury fills in the pores, you mechanically apply the load, mercury fills in, and you measure how much of mercury. So mercury is a non-wetting liquid, so the contact angle between mercury and the surface is higher than 90 degrees. It's typically about 110, 120 degrees depending on what you have. A wetting liquid have a contact angle lower than 90 degrees. This is probably in some of the physics classes that you would have studied. And then same idea as a heterogeneous nucleation, you have different interfaces. Liquid vapor, liquid solid, and liquid solid vapor interface. Okay, now if I plot pressure, I don't think I have a pressure picture. Let me see if I have a pressure picture. No. Okay. That's fine. So if I plot the diameter of the pore, now there's an equation called Washburn equation. Washburn equation relates pressure to the size of the pores. Very simple equation which just says the pressure or size of the pore or pressure is inversely proportional to the size of the pore. So if I want to enter a really small pore, I need a higher pressure, right? And then pressure is proportional to the contact angle. Pressure is proportional to the surface tension. Pressure is inversely proportional to the radius. P is equal to 2 sigma cos theta over r or 4 sigma cos theta over r. Simple, very simple, straightforward. I'll have it somewhere else. So this is the intrusion curve. So I'm intruding mercury. So you start from here, the larger diameter pores get intruded first, right? And then you sequentially go into smaller and smaller diameter pores. And then you extrude, you try to take the mercury out. Now typically people do only this part. You won't see the top part in many of the papers or literature. They just intrude and find out, okay, you go here, maximum, roughly about 0.14 cubic centimeter per gram. I'll find out the density of that piece, put it in a pyrometer and find out what's the density of that cement paste, say 2 grams per cc. 0.14 times 2, 0.28 is my copper oxide, 28% per oxide. That's how you find out the total cost. And then, of course, I can find out how much volume in each of those diameters, right? This curve will tell me how much of volume is in this 0.1. Again, it's cumulative, so you have to account for, you have to subtract for every sequential step. But you can find out cumulatively, between 0 and 0.4, if you can find out, I'll say, yeah, at 0.04, my size is about 0.018 microns. So you can find out what is the size, corresponding size of the pore. So this is the intrusion curve. Now, when mercury intrudes into a pore, and I'll talk to you about some drawbacks also. When mercury intrudes into a pore, if I exert pressure to put something in, if I release that pressure, should I get what I put in also back? Theoretically, yes. But am I getting everything back looking at that picture? Am I coming back to zero? I'm leaving some mercury in the system. Why is that so? Huh? Entrapped between pores, we'll come to that. The way it went in, well, you're extracting that, so you're not giving any energy, you're just taking the pressure off. So from a pressure balance, you've balanced it, but energy balance is not complete. But also, the other idea is that some mercury gets entrapped between pores. So for example, you have a large pore constricting into a small pore, becoming a large pore again, right? This large pore got drained, this large pore got drained, whatever is a real small thing in between, it just stayed there. So, what does that tell you? What does that tell you? Then, if that is the case, what does this test, what can this test be used for? To find out how complicated the pore structure is. When will you make the pore structure more complicated? By adding what kinds of things do you make the pore structure more complicated? Fly ash, silica fume, things like that, right? So now, extrusion is a good way to find out the ratio between intruded and extruded volume is a good way to find out how. If all my pores are direct cylinders, what will happen? My extrusion intrusion will be the same, right? If the pore structure gets complicated and complicated, I will have more and more differences between extrusion and intrusion. That is one way. So if you take an OPC paste, take a fly ash paste, you will see the difference. And I've shown you here with some limestone, you see the difference between extruded and intruded volume, right? The more difference between extruded and intruded volume, you will see that there is more complex pore structure. More complex pore structure, good or bad? Good for strength, doesn't matter. So you want to create a more complex pore structure. Even though it's hard to measure, hard to quantify, you want in concrete a more complex pore structure. And the more complex pore structure can be engineered by using will in turn give you common. So this is your intrusion-extrusion curve. Now, if I take the derivative, there are a lot of things that you can do with this curve. If I take the first derivative of this curve with respect to diameter, intruded volume with respect to diameter, log diameter, you get a certain spike in the curve. So this is OPC, this activated slag. You will see a certain location with a spike, with the first peak. That is called the critical pore size. That is called a critical pore size. Now, a critical pore size, and that's another thing that MIP is useful for. You will get a specific value of a critical pore size. Now, what do I mean by critical pore size? It is the pore size, and I'll talk to you about percolation probably tomorrow. But it is that pore size beyond which fluid flow can happen much more easily. So a critical size is a size beyond which percolation or connectedness in the pore structure will happen. Okay? So now again, connectedness is a very abstract concept in the pore structure. Have you guys played, it used to come in all the newspapers, it might even come now. Or if you're on the airplane, you will say, how will the fox find the way to his house? You've done things like that. That's exactly the idea. In scientific language, we call it the burning algorithm. Okay? The exact same thing, and that's why I made kids do all these things, okay? So that when you have to teach them concrete later on, it makes it very easy. You see this, right? Rabbit has to find the way, go through all this, and then if you go to some exhibitions, you have mazes where you have to walk through, and you keep walking through, you don't know how to go out. Right? So this is exactly the same thing. If you have a concrete, and water comes from one side, and water wants to come to the other side, so permeate through, this is exactly the kind of path the water is taking. Right? This is very tortuous pore structure. Water is like all of us. It's a very lazy thing. It finds the path of least resistance. If somebody says there's a highway there, we'll only drive through the highway, never through the surface streets, right? Because there's no traffic lights in the highway. So water does the same thing. Water goes through the path of least resistance. So you will have this very tortuous pore structure through which the water or the ions go through. But if the pore size is really small, the transport takes a long time, right? But when the pores get to a certain critical size, you can theoretically and experimentally prove that there is what we call percolation. Percolation basically means I can go from one end to the other with no blockages. Of course, I may have to go zigzag, but I can go from one end to the other like you do your little things in the game, right? You can go from one end to the other. Once you get to that critical size, that's when we say that we have percolation, we have gotten percolation. Therefore, the more to the left this curve pushes. Now think about it. Now this OPC and alkali activated slag, really no difference in the size, right? But more to the left this peak pushes, what will you know? The percolating pore size is much smaller, which means even at a smaller size, it's all connected completely. The more it pushes to the right, you say I need a larger size to be connected. Again, you can differentiate between mixes that have fly ash, mixes that have silica fume, mixes that have something else, alkali activated slag, alkali activated fly ash. With a little bit of calibration, with a little bit of knowledge about how this happens, now this becomes a very powerful tool to figure out what microstructural changes happen because your constitution composition has changed. Are we ready for lunch? Yeah. Is it right? Lunch ready. Lunch ready. So I'll leave you with one thought to think over lunch. One thought to think over lunch. In the manufacture of anything that you ever do scientifically, okay? In the manufacture of anything, you are manufacturing something because you need that thing to perform a certain function, right? You're doing concrete to perform a certain function. You're doing steel to perform a certain function. You're doing a composite to perform a certain function. The functions could be different, but you want to do something, right? You never manufacture anything just like that. Why have you made this? So just like that, I had time and I had money. I just made this. I don't know why. Nobody does it, right? So you do it for a property. If you are doing it for a property and if you are manufacturing something, you need two more things to make the process complete. One is my goal. I want so much of compressive strength. I keep saying compressive strength because even though I say that's not correct, but I'll tell you because that's what everybody uses, okay? So I want a 40 megapascal compressive strength. That's my goal. That's what I want in the material. But based on that, I know what I need to as compositional starting points to make the 40 megapascal concrete. So I need the compositional correctness. If I want 40 megapascal concrete, can I start with just pure fly ash and mix it with water and get 40 MPa concrete? No, I know the composition of fly ash is not good enough to give me by itself to give me a 40 megapascal concrete.